Now, as I mentioned before that we are going to have a two tutorial discussions. One has already been discussed by Dr. Maiti. So I'm sharing my screen to quickly have a solutions for the robustness using the very famous Kharitonov theorem. Can someone from the participant side confirm whether my screen is visible or not?
Visible, sir.
Thank you. So let's quickly revisit the merits of this problem. So far we have discussed or came across this robustness words when we talk about the designs and the study of the feedback control system. So although the robustness and the resiliency sounds very similar, but if you go into the definition of these two keywords, you will find out a significant difference. So robustness is the ability to maintain satisfactory operating conditions or satisfactory operations during any type of contingencies. While the resiliency is defined or rather quantified as an ability of the system to withstand and recover from any undesirable operating environment. So in this context, I can cite a very famous quote by Nelson Mandela, through which the definitions of the robustness can further be explored. What he said, "Do not judge me by the success, judge me by how many times I fell down and got back up again." So this is what the robustness is. We don't have any means through which the disturbances or the uncertainties can be ignored, because they are there in the physical systems inherently. So what we can do, we can make our feedback control system so much rich so that whenever there is any unwanted inputs or unknown inputs in the systems, your systems can satisfactorily maintain its operations. So in the literature or the state of the art, to study the robustness, different algorithms have been well reported. One of the famous control algorithm is the H infinity control, which is also going to be discussed in this course later. But as far as the today's tutorial is concerned, we are just going to study the robustness of a so-called linear system with the help of Kharitonov theorem. Now, before we apply the Kharitonov theorem to any LTI system, so-called LTI systems, what we have to do at first, we have to formulate the characteristics polynomial, or rather interval characteristics polynomial, for proceeding with the Kharitonov algorithms. So if I recall the linear control system theory, we all are well familiar with the Routh-Hurwitz criteria. We know in the Routh-Hurwitz criteria, the first step that we have to do once all the sufficient conditions are met to formulate the characteristics polynomial. which is 1 plus g into h equal to 0. That is the characteristics polynomial of a so-called LTI systems that we can easily formulate in the case of Routh-Hurwitz criteria once all the sufficient conditions were fulfilled. Now here we are going to formulate the characteristics polynomial, but we are calling it as an interval polynomial. The reason is very simple. What it is stated in the literature that a system which is operating at a nominal conditions, now when the system is subjected with any type of unknown inputs or uncertainties or perturbations which disturb the nominal operating conditions or nominal operating point, the deviations is supposed to be nearby of the nominal conditions. So what we are assuming that the system operating point is perturbed about the vicinity of the nominal situations. So as you can see here, we have defined the characteristics polynomial with the PS argument because we are doing the Laplace operations all. So which is defined in this particular form. Dk is the coefficients of the polynomials and S is the Laplacian operator. So what we are assuming in the case of interval polynomial, this dk, the coefficients of this characteristics polynomial, is bounded between dk minus and dk plus. So it has its lower bound as well as upper bound. So with this knowledge, what we are doing, we are characterizing this polynomial into 4 polynomial equations q1 to q4, which is follows this particular definitions. So what Kharitonov stated, if I go for the study whether my feedback control system is robust towards a given uncertainty, only we have to formulate 4 Kharitonov polynomial from the given characteristics equations. Obviously, the upper bound and the lower bounds or the variations, the extreme points are available to us. So following these definitions, what we can do, we can easily compute this q1 to q4 polynomial from these from these polynomial equations. Now, what these polynomials, these 4 polynomials signifies in the complex frequency plane. These 4 polynomials are nothing but the 4 vertices of these rectangles. So if I placed or if I compute this Q1 and Q2, Q3, Q4 for a given frequency, then these are basically represented by these 4 vertices of this rectangle, what is very famously known as Kharitonov rectangle. Now, once these polynomials are available, then what we can do, by changing this frequency omega, we can have a variations or various types of rectangle plots in the frequency domain, complex frequency domain. So while you change the frequency from some given value to the another label, what we will find? We will find a family of this type of Kharitonov triangle in the complex frequency plane. Now, once this family of Kharitonov rectangles are available with us, then based on what criteria we can conclude the closed loop system for a given perturbations level is robustly stable. So for this, we are having two test practices. The first statement says, individually test Q1, Q2, Q3, Q4 are Harwich or not. So what they said, individually test all these four polynomials are passes the Harwich test or not. This is the first statement. Here it is K1, K2. So K1, K2, K3 are same as the Q1, Q2, Q3. And the second statement is based on the zero exclusion principle. What they say is, for a given frequency, we will have a Kharitonov rectangle in the frequency plane. And once I change the frequency, what I will get a family of Kharitonov rectangles in this frequency plane. Now they say, just observe whether the origin or 0 point is included by this Kharitonov rectangle or excluded by the Kharitonov rectangle. If the 0 point is excluded by the Kharitonov rectangle for a given frequency range, then it concludes that your feedback control system performs robustly for a given uncertainty band. So as you can see in this particular simulation plot, for a given frequency range, we are having a family of Kharitonov rectangles in the complex frequency plane, and a zoom view of these sections is available here. What it implies that this 0 is excluded by the Kharitonov rectangle. So whatever be the example that we have taken to plot these things, for that system only, I am concluding that the 0, since the 0 is excluded by the Kharitonov rectangle, that implies my feedback control system is robustly stable for the chosen dk minus and dk plus. So this is a very simple test. Now, we have taken two numerical examples to demonstrate the Kharitonov theorem for the robustness study. So, here is a polynomial P. Basically, it is an interval polynomial. Unlike the polynomial what we had in the Routh-Hurwitz test, if you recall, that is a function of S only. But here, this characteristics component, this P, is a function of S and Q. Q is this function, or you can think about it as a function of D. So Q is this coefficient whose upper bound and lower bounds are provided or calculated based upon the design knowledge. So a simple third order characteristics polynomial, interval characteristics polynomial is given to us, and we have been asked to test whether the closed loop system for which this characteristics polynomial is computed is robustly stable or not using the Kharitonov approach. So for this Kharitonov polynomial, following the same guidelines available in the literature, we were computed 4 Kharitonov polynomial starting from K1 to K4, or you can write it as per the notation Q1, Q2, Q3, and Q4. Okay. Now, as stated by the Kharitonov algorithm, what we can do, we can test this 4 polynomial individually, whether they satisfied Harwich conditions or not, or we can refer to the zero exclusions property. So these are the steps which we have followed to simulate this problem in the MATLAB platform. So what we did, we defined these 4 polynomials in the MATLAB platform. Then we were substituted S by j omega because we are looking for the frequency response analysis only. So the attenuation component was taken absent. And while you put S equal to j omega here, we will get a real component as well as imaginary component. So that we are going to separate. Then Kharitonov's rectangle were plotted for a frequency range 0 to omega 1. Omega 1 can be any value based on your choice. And then we have to check whether the origin is excluded or not. So we were simulated this simulated this problem in the MATLAB platform. So as you can see, for a given frequency range, this is the origin or 0 point, and this family of rectangles are rotating. If you can see the rotations of these rectangles, you will find out these are rotating in a counterclockwise directions, starting from the initial frequency to the calculated frequency. And these rectangles are not including this 0 point or origin point. So invoking the zero exclusion principle of Kharitonov's theorem, what we can conclude that the system for which this interval polynomial has been derived, of course, a closed loop control system for which this interval polynomial has been derived, is a robustly stable system as far as this test is concerned. Next, we also have tested another problem which is described in this slide. So as you can see, a closed loop control system is given to us. So this is my output y of t, or it is in a S domain, so let it be y of s. So this is the plant which is followed by a controller, and we are having a negative feedback as usual in the control theory. Now this GS is characterized with these transfer functions. Okay, so it's a third order system without a doubt, and we also have given the variations of the coefficients. So as you can see, there are 6 unknowns in the in these transfer functions, and their upper bound and lower bounds are well specified in these numerical examples. So for this case, what we did, we were taking this controller simply as a proportional controller with a gain of capital K. Okay, now by simplifying this closed loop system with the help of signal algebra, we can easily compute the closed loop transfer function Ts, which is Gs into Cs over 1 plus Gs into Cs. And 1 plus Gs into Cs is the characteristics polynomial. Just substitute Gs is equal to this. Then substitute the N0, N1, N2 like this I am writing down here. So we have the characteristics polynomial as Cs is K. So K into Gs is equal to 0. Gs is substituted here. So Gs involves all these coefficients. Considering their upper and lower bound, what you can represent? We can represent the polynomial as a function of S and coefficients. That is an interval polynomial. Then from that polynomial, 4 Kharitonov's polynomials have been computed, and the objective is to find the value of K for which this closed loop system is robustly stable for a given uncertainty band. Then we were simulated the problem and we come out with the conclusions, because we know that the Routh-Hurwitz test is the base test for finding out the range of any gain or a control parameter for which an LTI system is supposed to be stable. So it is come out that if I choose a K in the range of this, so this value is included, but the other side is open. So for this range of K, if I solve the interval polynomial in a MATLAB platform, it finds, or it's seen that this origin is excluded by the Kharitonov rectangles, which demonstrate that the system is robustly stable for this given uncertainty band if the gain of the controller is chosen somewhere following these stability conditions. So this is a very simple test through which the robustness of an LTI systems can be demonstrated. However, in the real-time practices, we are actually dealing with nonlinear systems. So for those nonlinear systems, this type of algorithm is not applicable. So for which, if I want to achieve a good robustness, then I have to consider some advanced robust control algorithm, maybe the sliding mode approach, or H infinity control, or mu synthesis like algorithm for ensuring robustness of the developed closed loop control framework. So I can show you the simulation results. Yeah. So, but I have to show you the code. Okay, so we have followed the same steps which I have mentioned in my PPT, that we were defined the 4 Kharitonov polynomials which were calculated from the given interval equations. Then by substituting S equal to j omega, we were separated the real and imaginary component of the K1, K2, K3 and K4, and then by using this single line, we can plot the rectangles, Kharitonov's rectangle for a given frequency. So the frequency were chosen from 1 to 5 with a interval of 0.1. You can have your own choice. So within this frequency range, all the rectangles were plotted in the complex frequency plane, and because of which we are getting the family of Kharitonov rectangle, and then just seeing the plot whether this is origin is excluded or included. So as you can see here, the same results which I have shown in the slide. This is the origin 00 point and it is excluded. Whatever be the frequency that you choose, always it will exclude, because the motions of this rectangle is counterclockwise only. In the same line, we have solved the second problem, the same procedure that we have followed. Yes, K1, K2, K3, K4 were defined. These are defined from the given polynomial equations. Then we were separated the real and imaginary component, and again we were plotted this Kharitonov rectangle for individual frequency, which were considered in this for loop. This also shows the results. So if you have any queries, please ask me. I will happy to answer. But yes, this is a very simplified approach that one can use in their system if it is a linear type. But if it is not a linear or it is time varying, then definitely this type of algorithm will no longer be applicable. So with this, I am concluding. If you have any queries, please let me know.
Yes, sir. Good
Please.
evening, sir.
Very
I have
good
one
evening.
question. While tuning, so this algorithm doesn't provide me the tuning aspect. This again is a hit and trial method only. Am I right, sir, in understanding?
So far, I don't know whether you followed the slide or not. I clearly mentions that we are talking about the fixed gain controller. I mentioned somewhere, yeah. It is a fixed gain controller that I have taken into account. The tuning means I don't know. There are two ways of defining the tunings. The number one is that beforehand you have computed the optimized value of your controller parameter by conventional approaches or any classical approaches like Ziegler-Nichols and all. Whichever method you are going to apply for finding out the controller settings, those settings are fixed only. They are not a function of time. Okay, so yes, once you have tuned the parameter, that's why I said in that second problem that we were calculated the range of the k for which the system is supposed to be a robustly stable. So that we have calculated well in advance. And within this range, whatever the value of k that I'm going to fix there, the system is performing robustly stable. So the tuning is, this is one way of defining the tuning. And the second way of defining the tuning, what we famously consider as an adaptive control. Your parameters are automatically updated based upon your measurement or environmental conditions. That is also a tuning. But in that case, your parameter is not a fixed. It is a time dependent one. Whatever the measurements or environmental situations you are getting, in order to attain the stability, your controller parameter has to be changed or updated or tuned. So that is another way of defining tuning. So if you're dealing with the fixed gain controller, then definitely it is assumed that you already have well tuned your PID parameters or PI parameters or P parameters, and then we were derived the characteristics polynomial. Are you getting my answer?
Fine, sir. Okay, sir. Thank you.
Anything else? This is only a testing your control system is robust or not. So while you are going for a testing, it is assumed that you already have designed your controller. That means the tuning part is already done.
Done. Got it. Correct, sir. Got it.
Thank you all. And with this, we are concluding day 2 of this GYAN program. And I appreciate all that you people have attended the sessions thoroughly. So if there are no further queries, we are going to conclude the sessions here. As per the schedule, tomorrow's sessions will also start from 14 hours IST.